think it.
Yeah.
Okay, yeah, it's working. Yeah, okay, perfect. Thank you. So basically we're starting with the basics of NMR for those of you who aren't really experts in the NMR field. So NMR is based on the macroscopic mechanization that originates from a very, very large collection of nuclear spins. And so, there we go. So if we have like a human brain, human in a magnet, the vertical lines are the magnetic field. If we look at a very small volume, for instance 1 microliter, in that 1 microliter there's literally billions and billions of proton spins. In other words, small bar magnets, if you will. Every proton nucleus behaves as if it was a bar magnet. Now, the far majority, 99.99% of those nuclear spins, they have a random orientation. So if you add them all together, the sum of those magnetizations basically adds up to 0. They do rotate around the main magnetic field in many megahertzes, but you don't get any signal from it. Fortunately, there is a very small amount of spins that are biased by the external magnetic field. So they are biased to having a slightly more parallel orientation to the B0, and those are the spins on the right. And when you add those together, they again cancel in the XY plane, but they form a macroscopic magnetization vector along the Z-axis. And that is ultimately the signal that you detect. Now in NMR we don't detect the signal along the Z-axis, but we try to rotate it into the XY plane. For that you need a secondary magnetic field, B1. That's a very small magnetic field, but it is applied at a Larmor frequency. So the B1 field also rotates around in many, many megahertz, the same frequency as the spins. Because they are perpendicular to each other, the magnetization M0 will experience a torque and it starts to rotate around the B1 field. If you now adjust the flip angle to be 90 degrees, it's set to be excited into the XY plane. At that point you can turn off the B1 field and the magnetization M0 starts to rotate around in the transverse plane. If you put a little receiver coil in the transverse plane, then the rotating magnetization in the transverse plane induces a little bit of a voltage in that coil, which will ultimately be your NMR signal. So that's the very basics of NMR, but on a practical everyday level, NMR is really concerned with the detection and separation of those frequencies, of those Larmor frequencies. And that is of course because of the Larmor equation, where you have your Larmor resonance frequency in megahertz, which is directly proportional to the main magnetic field B, which is the magnetic field strength in Tesla. And if B is, let's say, 3 Tesla, then the Larmor frequency for protons will be 128 megahertz. And that is because that constant, gamma, which is a gyromagnetic ratio. And that basically scales the frequency linearly with the main magnetic field B. Now, if we now look at resonance frequencies at 7 Tesla, then you will find around 300 megahertz, in this case 298 megahertz, you'll find signal from protons, because protons have nuclear spin, they can form the macroscopic magnetization, and they resonate at 298 megahertz. If you go a little bit lower in frequency, at around 120 megahertz, you'll find another signal which originates from phosphorus nuclei. They also have a nuclear spin. Go a little bit lower, you see sodium signal, a little bit lower you see carbon-13 signal, and a little bit lower again you find deuterium signal. Now if this was all there was to it, NMR would not be the very powerful technique that it is today. There is another detail that is very important. So if we now move this up and we zoom in a little bit around the frequencies around 298 megahertz, we will see that it is not a single frequency, but there's actually a whole bunch of little frequencies if you acquire this from the human brain. Now that effect is so-called chemical shift effect, and that is a very small effect. If you look at the axis, there's only a few hundred hertz on top of 298 megahertz, but it is a very reproducible effect, and that gives rise to spectroscopy and ultimately also to imaging. You can also look at the other frequencies. If you zoom in on the phosphorus, 120 megahertz, you can also see there's a whole bunch of frequencies, and that is true for all of these nuclei. So where is this coming from, this chemical shift effect? So let's look at a hypothetical example of a single proton nuclear spin in an external magnetic field. The magnetic field experienced by the nucleus, Bn, is equal to the applied B0 field. And you're going to get a peak at the Larmor frequency. Now, you're never going to have just a single proton nucleus. You're always going to have an electron cloud around it. The electron cloud will generate its own little magnetic field locally that opposes the B0 field. In other words, the field experienced by the nucleus is slightly reduced. If the field is slightly reduced, the Larmor frequency is slightly reduced, and you're going to get a peak at a lower frequency. You can see that here, the horizontal axis can be interpreted as Larmor frequency, resonance frequency, but that is of course proportional to the magnetic field at the nucleus, and that is again dependent on how much shielding is provided by those electrons. The more shielding, the higher the field at the lower the field at the nucleus, and therefore the lower the resonance frequency. Now, a more realistic example, this proton is attached to a larger molecule. The larger molecule will have electronegative atoms like oxygen that likes to draw electron density towards itself, reducing therefore the electron cloud density, reducing the electron shielding effect, and therefore increasing the magnetic field at the nucleus, and therefore increasing the resonance frequency. And so you can see from this example that the exact frequency in NMR is extremely sensitive to the chemical environment of the nucleus spins. And therefore you can detect different chemical groups and different chemicals by their unique frequency. Now, the original Larmor frequency, the Larmor equation that I gave was frequency is proportional to B0. That is true, but to make it more general, the Larmor frequency is proportional to the magnetic field experienced by the nucleus, and that includes those chemical shift effects. Finally, the final thing about the basics is how we're going to display these kind of spectra. So let's have a look at lactic acid. Lactic acid has 4 protons that you can detect directly. There's a single proton in blue, and there's 3 metal protons in red. Because of difference in electronic shielding, the blue proton typically is at a higher frequency, and the 3 metal protons have an increased electronic shielding, and therefore they resonate at a lower frequency. Now, this would be the spectrum that you get at 3 Tesla. It's around 127.5 megahertz, plus or minus a little bit. The big numbers, that's not very easy to talk about. And it gets even worse if you do the same experiment at 7 Tesla. You're going to get the same spectrum, but now the numbers are 298 megahertz, plus or minus a little bit. Now, if 2 researchers are talking to each other, and one has a 3 Tesla and one has a 7 Tesla, it's going to be very difficult to talk to each other, because first of all, you have very big numbers with small deltas on top of it, and in addition, they're different numbers. So how do you know which number corresponds to which peak in the spectrum? Now, to solve that problem, typically NMR spectra are displayed on a ppm scale. Now, let's have a look what that means. At 3 Tesla, the Larmor equation is 127 megahertz. 1 part per million, therefore, is 127 hertz. If you look at the frequency difference between these 2 peaks, at 3 Tesla, it is 357 hertz, and that therefore corresponds to 2.8 ppm. At 7 Tesla, the delta is 836 hertz, but that also corresponds to 2.8 ppm because the number of hertz in the ppm is higher at 7 Tesla. So now the frequency difference between the 2 peaks is identical at both fields when you express it in ppm. So then the only thing that you still need to do is, where do we define 0 ppm in this spectrum? And then you're good to go. Now, 0 ppm is typically defined by this molecule. It has 9 equivalent protons, and it is basically defined that the peak from those 9 protons resonates at 0 ppm. Once that is defined, everything else falls into place. Then the lower frequency lactate peak is always at 1.3 ppm, no matter what field you are, and the higher frequency is always at 4.1 ppm. And so it's very easy now to communicate with each other, because that peak is always at 4.1 ppm. Of course, you do have to realize that the horizontal axis is really a frequency axis in megahertz. This is just a convenience scale. Okay, so let's now switch to the problem that this workshop is about, spectral overlap and what to do about it. So this is a proton spectrum from human brain. There's a lot of information content in there, but there's also a lot of peaks that are overlapping with each other. If we look at this part of the spectrum, there is creatine in red and there's GABA underneath. And you cannot really separate GABA very easily from the creatine in this case. Similarly, that creatine peak is overlapping with a phosphocreatine peak. They are so close to each other, it's almost impossible to separate. A little bit further down in the spectrum, you have glutamate and glutamine. They are partially overlapping at high field, but they're completely overlapping at low field. And this problem there's another thing here. Basically, every peak in the spectrum is overlapping with broader signals from macromolecules. Now, this problem of spectral overlap is not unique to proton NMR. If we look at phosphorus NMR spectra, then you can see that in the blue box there's also a number of peaks, ATP, NAD+, NADH, and UDPG. They are basically partially overlapping with each other as well. So looking at one of those compounds, you have to deal with the other compounds. So now the question is, let's say we're interested in GABA detection. What are we going to do about it? Because there's a big creatine peak on top of it. Well, one thing you could do, which is an expensive solution, but it works quite well for some molecules, is to basically go to a stronger magnet. So here are simulated spectra for glutamate and glutamine. At 100 megahertz, they basically overlap at every position. But if you now increase your magnetic field strength higher and higher and higher, and the highest one is 11.7 Tesla, or 500 megahertz for protons, you can see that around the 4 position, the glutamate and the glutamine are now fairly decently separated. So basically, just going to a stronger magnetic field basically pulls these frequencies apart, and you can separately detect them. Now, this is an expensive solution, as I mentioned before, but it also doesn't work all the time. For example, GABA and creatine will be perfectly overlapping at every field, so this is not a solution. Another thing you could do is to utilize differences in T1 and T2 relaxation. If you look at 3 compounds here, NAA, total creatine, and macromolecules, if you increase the echo time, you can see that the macromolecules disappear very quickly. They have a very short T2, whereas the 2 metabolites have a much longer T2. And so if you now acquire a spectrum at a short echo time, you can see that all of the peaks are on top of each other. If you now acquire a spectrum at a longer echo time, you can see that the macromolecules have completely been removed, and you can only see the metabolites, NAA and creatine. So this is one way of removing one of the overlapping compounds. You can also use differences in T1 relaxation. In this case, you first invert all of your magnetization, and then you wait a certain amount of time. If you wait until this point in time, you can see that the macromolecule signal goes through 0. So if you excite the signal there, you basically have no macromolecules in your spectrum, and you just have the metabolites. If you wait a bit longer, then the metabolites go through 0, and you can get a macromolecule spectrum. Very nice method to separate metabolites from macromolecules, because there's a big difference in T1 and T2. Not a great method to separate creatine from NAA, because the T1 is almost identical. So if you want to separate metabolites, then the most powerful method out there, and that will probably be discussed throughout this afternoon, is basically using spectral editing based on scalar coupling. Now, I can fill a whole lecture with just what scalar coupling is. We're not going to do that, but I'm going to just give you the brief overview. So let's say you have 2 nuclear spins, a red one and a blue one. They are basically interacting with each other in many, many different ways. An important one is basically random through space interactions. Each nucleus generates its own little magnetic field, as you can see, and as they tumble around in space, one magnetic field of one spin affects the other spin, and that basically leads to T1 and T2 relaxation. Nevertheless, if you get an NMR spectrum from these 2 compounds, you basically get 2 signals at their own Larmor frequency. Now, besides random through space interactions, those molecules or those nuclear spins can also interact with each other in different ways, especially if they're part of the same molecule. So now the red and the blue one are part of the same molecule, and they're basically very close to each other. And the green ones are the electron spins in the chemical bond. Now you get an effect that is called scalar coupling, where the orientation of one spin has an effect on the frequency of the other. So in this case, when the red spin is up and parallel to the main magnetic field, the blue one has a slightly lower frequency. If you now have the situation where the red one is down or anti-parallel to the B0 field, then the frequency of the blue one will be slightly higher. In other words, where we had only one frequency when we didn't have this effect, in the presence of this effect, that one frequency, nu1, is now going to be split in two peaks, nu1 minus a little bit and nu1 plus a little bit. And you're going to get a spectrum like this. Now, if the blue one is split up by the red one, then the red one always has to be split up by the blue one as well. You cannot have one without the other. So if you have a split signal in the spectrum somewhere, then somewhere else there needs to be a split signal as well. They always go together as a pair. Now that is scalar coupling, and that is something you can utilize to achieve spectral editing, because there are molecules that have scalar coupling, and there are other molecules that don't have scalar coupling. That is an absolute difference, and therefore you can expect to achieve an absolute separation between these two molecules. Now, how do you utilize it? You basically utilize it with a spin echo sequence. You can see here 90-degree delay, 180-degree delay. If you now have a molecule that does not have scalar coupling, like water or creatine, then no matter what the echo time is, the signal will always be up and positive, as you can see. The signal will go down in amplitude because of T2 relaxation, but it will always be up and positive. Now, if you now have a scalar coupled spin system like lactate or GABA, then you're going to get an interesting effect where the doublet signal, that's how it's called, if you have two signals that are scalar coupled, that's called a doublet. The doublet signal can actually become negative. At the very bottom echo time, you can see that that doublet signal is now inverted relative to a signal from a molecule that doesn't have scalar coupling. And that is something that we can utilize. In the middle echo time, the scalar coupled spin has zero intensity. There is as much negative intensity as there is positive intensity. That is also something that can be used by a different type of spectral editing. Now, this is half of the story. There is another half where you have to acquire signal with a so-called selective spin echo. It's the identical sequence except the 180-degree pulse is now selective for one of the two doublets. If you remember, if you have a doublet somewhere in the spectrum, then you will have another doublet somewhere else in that spectrum. This 180-degree pulse is selective for one of the two. If you do that, then for molecules that don't have scalar coupling, nothing changes. If you increase the echo time, the signal stays up and positive all the time. But now for scalar coupled spin systems like lactate and GABA, you can see immediately the difference with the previous slide, that now that signal is always up and positive as well. Whereas with the non-selective spin echo from the previous slide, you had echo times where that doublet was inverted. So that is now something we can utilize. The way we do that is with so-called J-difference editing, where you have to do two experiments. One is your regular non-selective spin echo, and one is your selective spin echo. Now, the sequence is basically able to do that. If those selective 180-degree pulses, those shaped 180-degree pulses, if they are not there, it is a regular spin echo. And if those 180-degree pulses are there, it is a selective spin echo. So let's have a look at the example. We are interested in the molecule with nuclear spins I and S, but both of those are overlapping with lipids and with water, so they are not detectable. Let's now do our editing experiment. First, we do our normal non-selective spin echo. You can see that the spin S is been suppressed by the water suppression, so you cannot see that. More interestingly, the spin I with this echo time is now inverted. All the other molecules which don't have scalar coupling are up and positive. Unfortunately, this is not going to help you because the spin of interest, I, is still overlapping with the other spins. Therefore, we need to do the second experiment, which is now a frequency selective spin echo, in which we selectively refocus spin S. The result being that spin I is now up and positive. All the other spins in black were up and positive on the left spectrum, and they're still up and positive. So now J-difference editing, calculate the difference between those two spectra. You basically cancel out all of the black lines, and you end up with the compound of interest, spin I. The nice thing about J-difference editing is, because you have stored both experiments separately in memory, you can also calculate the sum, and therefore you still get all the other peaks in the spectrum as well. So you don't throw away information, you basically get additional information. So this is how you do it theoretically. practically it's a little bit more complicated because you need to add spatial localization. So this is the most well-known sequence, so-called mega press. So the localization is of course achieved by press. The 90, 180, 180, those are the voxel localization pulses. And then the two shaped 180-degree S pulses are the ones that are turned on and off to achieve the editing. And of course, in addition, you're going to have water suppression in front of this sequence. An equally popular sequence is the mega laser or mega S laser, semi-laser. Now you're going to have the 90, 3 180s and final 180. Those achieve the spatial localization, and then the 180-degree S pulses are turned on and off again to achieve the editing. Okay, so let's have a look at one of the examples. We want to see GABA. So this is our proton spectrum again. We know that GABA is resonating at these three peaks, at these three frequencies. And so now the first question becomes, which peak do we want to observe? H2, H3, or H4, sorry. Now, then it becomes a question of what are the overlapping, compounds. Now, if you look at H2, H2 is overlapping with glutamate H4 and H3. GABA has scalar coupling, glutamate has scalar coupling. So there's no absolute difference. So then you cannot really expect an absolute separation either. So normally H2 is not used because it is overlapping with a scalar coupled spin system. If you look at GABA H4, that is to first approximation overlapping with creatine. Creatine has no scalar coupling, and therefore that is a really nice absolute difference. So we're going to observe GABA H4, and therefore the scalar coupling partner is GABA H3. So any kind of frequency selective RF pulse is going to be applied on H3 in order to get an effect on H4. So this is the experiment that you're going to do. First you're going to get a selective spin echo in which you selectively refocus GABA H3, which is very close to the NAA signal, so that's why the NAA is gone. But more importantly, the GABA H4 that is underneath the creatine is basically up and positive. This is now a triplet signal because it has more protons, but the principle is the same. If you now do your regular non-selective spin echo, you're going to get your NAA back because you don't have your frequency selective 180-degree pulse. More importantly, the GABA underneath the creatine is now partially negative. It turns out that you cannot fully invert GABA, you can only partially invert GABA, and this is the best that you can do. But the principle is the same. If you calculate the difference between these two, you're going to get a nice GABA peak that was originally underneath the creatine, and now the creatine has been removed. Do the experiment again, like the next day, and you're going to basically get the same result. Now, I do need to notice there's a few peaks in red that really, you didn't expect that. At least the first time I did it, I didn't expect that. And so that is so-called co-editing. Those signals are basically also edited out. Now, why does that happen? Because the glutamate H2 is, of course, coupled to glutamate H3, which is very close to the GABA H3. So if you apply the frequency selective RF pulse to the GABA H3, you also affect the glutamate, and therefore the glutamate is also edited out. Glutamate is at a different frequency, so it doesn't really matter. The NAA appears there because you apply the editing pulse there, directly affecting the NAA in the first spectrum, not in the second spectrum, and therefore you don't subtract it out cleanly. Again, the NAA is at a different frequency than the GABA, so it doesn't matter. There is a complication, however, that does matter, and that is originating from macromolecules. So let's have a look at the same spectrum again. We know that the GABA is resonating there, and we want to look at the GABA H4 at 3 ppm. Now, it turns out that every in vivo spectrum from the brain for sure, but also other organs, will have a lot of macromolecule signals. They're fairly undefined, but basically they come from a whole collection of protein and other larger structures. So they tend to be a little bit broader. But they are fairly decently characterized in the sense that there are about 9 or 10 different resonances. One of the resonances, M7, is overlapping with GABA. Now, that would not be a problem if M7 is just a non-coupled spin system. It would just be subtracted out. Unfortunately, M7 does have scalar coupling. So let's have a look at the details. GABA is GABA4 at 3 ppm is scalar coupled to GABA3 at 1.89 ppm, and at J coupling, a scalar coupling constant, the separation in frequency between those two signals in a doublet of 7 Hz. Macromolecules, the M7 at 3.00 ppm is scalar coupled to a peak at 1.7 ppm with roughly the same scalar coupling constant. Now the problem now comes in is if you look at the profile in the upper spectrum of the editing pulse, that inversion profile is never perfectly selective. It is not possible in NMR to only invert one frequency. There will always be a certain bandwidth or range of frequencies that are inverted at the same time. You can see that from the width of that curve. Now, if that curve is narrow enough so that I don't affect M4, everything is good to go. Then M7 will be subtracted out and you don't have to worry about it. It turns out at field of 3 Tesla and below, it is impossible not to affect M4. You will affect M4. If you affect M4, you will edit out M7. Of course, GABA will also be edited out, and therefore the resulting spectrum will have GABA plus a certain amount of macromolecules. In the literature, this is referred to as GABA plus. You've got to realize that the plus is not a good thing, right? It is a bad thing. You have a variable amount of macromolecules, and it's up to you to be aware of that, and it's up to you to determine how much that actually is. But that's something to be aware of. Final thing that I want to say about like practical implementation of J-difference editing. As I told you, you have to do 2 experiments. If we're interested in GABA, GABA is a very low concentration compound, you need to average for, let's say, 25 minutes. So you can do it in a number of ways. You can acquire the first spectrum for 12 minutes, and then acquire the second spectrum for 12 minutes. That's the upper option. Or you can acquire one spectrum for 2 seconds, then the next one for 2 seconds, and then interleave that to fill up the 25 minutes. That's the bottom option. Now, if you have a perfectly stable system, either option will give you good results. The problem is, this is an in vivo system with large in vivo magnets. Nothing is ever perfect. And so in this example, I've basically measured the frequency drift of the magnet. So ideally a magnet is at 3 Tesla all the time, but it tends to drift a little bit. So it'll be 3 Tesla minus a few hertz over 25 minutes. In this case, you can see the frequency drift is about 7 hertz over 10 minutes. So if I ignore this, which you do if you run it in the upper or the first option, then you're going to get these kind of spectra. It looks pretty good, the upper spectrum. The lower spectrum is the difference between the 2 experiments, and you can see you have a reasonable looking GABA signal. However, if you look a little bit more closely where the red arrow is, there seems to be a subtraction artifact. That is exactly at the position where choline is, or total choline. Total choline has no scalar coupling, therefore it has to subtract out perfectly. It doesn't. If the choline isn't subtracted out perfectly, then the creatine is very likely not subtracted out perfectly either. And you're basically going to have GABA plus a creatine subtraction artifact. And that is because you ignored that the system isn't stable over time. Now, if you do take it into account and you acquire each spectrum and you store it separately in memory every 2 seconds or something like that, then after the experiment is done, you can frequency align all of those spectra. You can also eliminate some bad data. In this case, the subject sneezed once or twice. So those dots in red, they can be eliminated. Frequency align all of it. Then you're going to get these spectra. First of all, you can see that the peaks are higher because now they're nicely frequency aligned, and that eliminates line broadening. So you're going to get a nice boost in SNR. But now also the edited spectrum is clean. There is no subtraction artifact on the choline, and therefore there is no subtraction artifact of the creatine either. Okay, the final slide I want to show you is once you have your sequence, you're all done implementing it, and it works perfectly for GABA. This sequence will work for every compound with scalar coupling. All you need to do is change the echo time and change the offset of your frequency selective RF pulse. So for lactate, it turns out that the best echo time is 144 milliseconds. You want to detect lactate H3, therefore the editing pulse needs to be on lactate H2. Which is at 4.1 ppm. This is now a spectrum from a patient with a brain tumor. We weren't sure if that was lactate or lipids. If you do your editing, then you know for sure that yes, at least part of that peak is lactate. If you're interested in 2-hydroxyglutarate, which is another important molecule in brain cancer, it turns out that the optimum echo time is about 80 milliseconds. The offset is fairly similar to GABA actually, because GABA is at 1.89 ppm. And you're basically gonna, by adjusting the echo time and the offset, you can now edit for 2HG. Right? So this one sequence now opens up a whole avenue of different types of molecules that you can edit for. So to wrap up, I hope I've been able to show you that spectral editing based on scalar coupling is a very powerful technique to hopefully eliminate your overlap, or at the very minimum reduce your spectral overlap significantly. The nice thing about J-difference editing is it allows you, by calculating the difference, to get the compound that you want. But by adding the two spectra together, you get everything else. There's also other types of editing, multiple quantum-based editing, where you destroy everything except for the compound of interest. And so you would have to do a second experiment to get the other compound. So J-difference editing is very nice. Co-editing is absolutely the rule, and you need to be aware of it. For GABA, it is macromolecules. For other molecules, it will be other co-editing partners. And finally, you always have to be aware that you are working with in vivo systems. In vivo systems aren't perfectly stable. People do breed, people do move. There is frequency drift of the magnet. Shimming is always an issue, so there's something you have to be very, very much aware of. If you enjoyed my lecture, then I can encourage you to go to the YouTube channel, try to search for basics of in vivo NMR. At the moment I have 6 videos on there about basic things of in vivo NMR. They're short videos each, about 15 minutes, so they're small, bite-sized videos, and I'm planning to put a whole lot more up. And as already mentioned by the moderator, I have the 3rd edition of the book, where you can find all of these details and a lot more. And finally, I would like to thank you for your attention.